Good morning. I welcome you all for the last topic of the course on fluid dynamics and turbo machines, that is steam and gas turbines. In the last discussion lecture, we talked about compressible flows. So, now we will see what happens in steam and gas turbines, what are the different types of steam turbine configurations that we have, and the thermodynamic plots, the HS plots or the TS plots that are applicable for steam and gas turbines respectively. So, we will start today's discussion with an outline of a steam turbine plant. This is a typical layout of a steam turbine plant, which you have studied perhaps in the first level course on thermodynamics. Let us look at these numbers. We have the components pump, a boiler feed pump is there, which feeds the water to the boiler, where the water goes into the constant pressure heat addition, and then it goes to the turbine, and in the turbine we have the expansion and the work done. This turbine is connected to the alternator, which produces the electricity, and then the outlet of the turbine is connected to the condenser, and the cycle is repeated. So, this is the layout, and the corresponding the cycle is called the Rankine cycle, which you are familiar with. In this Rankine cycle, you can see that this is an ideal Rankine cycle. So, we are talking about isentropic expansion and compression. So, 1 to 2 is across the pump. So, this is the pump work that is required to be supplied. Then 2 to 3 is the isobaric heat addition that we are talking about in the boiler. 3 to 4 is isentropic expansion in the turbine, and 4 to 1 is the heat rejection in the condenser. The net work that you can get from this cycle is W T prime, that is the turbine work, minus the work added to the pump W P prime. Of course, there are other variants possible, and what we have shown the point 3, the state 3 is saturated vapor, it need not always be the case. That you have studied in thermodynamics, and I will not go into these details. So, to get the basics right, we can say that the pump work is given by, I am talking about specific work. If you want to get the total pump work, you have to multiply by the mass flow rate. So, is equal to H 2 minus H 1, which can be written because the density of water is about constant. So, we can write it as P 2 minus P 1 by rho water. The turbine work is given by H 3 minus H 4, which you already know from the discussions we had on thermodynamics, and also of course, from the thermodynamics lessons that you have taken earlier. So, the net work that we get is W T prime minus W P prime, which is nothing but H 3 minus H 4 minus H 2 minus H 1, and the heat addition is in the form of, we have written Q prime in, which is given by H 3 minus H 2, and we can say that the cycle Rankine cycle efficiency is given by W net prime whole divided by this Q in prime. Of course, we can substitute H 3, H 4, H 2, H 1 etcetera, and get a value for Rankine cycle. The difference between the Rankine cycle, which is for the steam power plant or the vapor power plants, and the gas turbine cycles, which is the Joule or the Brayton cycle that we will discuss, is the fact that in case of the expansion of steam, the end stage, that is the 4 in this one, is in the wet region. Even if you start from superheated point, let us say somewhere here in the constant pressure line, we can say that even if I draw it here, I can say that I will still end up getting in the wet region. So, this feature does not exist in case of gas turbines, and hence what is possible in gas turbine is one level of simplification, because we can also assume that the specific heat is constant. So, let us look at first the different gas turbine cycles that are possible and then the thermodynamic or T s representation of the same. This 3 to 4 prime I have shown is actually the process which will take place, which is not isentropic, and similarly you can have the pump work going from 1 to 2 prime, which is also an actual work, and you know already how to find out from the thermodynamic relationships the efficiency of the pump and turbine. We will also take up this aspect when we discuss the steam turbine in greater detail. So, this is the simple open circuit gas turbine. If you see, the air is taken in and the compressor, this is the combustion chamber where this high pressure slightly high temperature air goes in, and this combustion product goes through the turbine where it is expanded and it leaves. The turbine is coupled to the compressor and is connected to the alternator. Strictly speaking, this is not a cycle, because the states 1 and 4 are not connected and it need not be the same. So, an air standard cycles can be thought about, and this is a closed circuit gas turbine cycle in which this combustion chamber is replaced by a heat exchanger. The purpose is served by the transfer of heat to the gas to the air, and then it goes to the turbine, it expands and it gives out the heat and it is fed to the compressor. So, this is what we will see in the next slide, which is the thermodynamic representation of the closed circuit gas turbine cycle, which is called the Joule or the Brayton cycle. In the Joule or the Brayton cycle, before we go into that, let us see the numbers again. 1 to 2 is across compressor, 2 to 3 is heat exchanger, the constant pressure process heat addition, 3 to 4 is expansion in the turbine, and 4 to 1 is again constant pressure, but heat rejection this time. So, if I look at it, 1 to 2, 2 to 3 is heat addition, 3 to 4 is work done by the turbine, and 4 to 1 is heat rejection. So, now let us look at the compressor work W c prime. Again I am talking about specific work and not the total work. So, you have to total power out requirement, and in that case you have to multiply by the mass flow rate m dot. So, if I look at it, it is H 2 minus H 1, and look at the sign carefully. This H 2 minus H 1 is greater than 0, but this compressor work, as we have indicated here by the arrow, is the work done on the compressor, and so when we calculate the net work, we need to keep this sign convention in mind. And since we are assuming that this is a perfect gas, so we can say C p is constant, and we can write H 2 minus H 1 as C p times T 2 minus T 1. The turbine work can similarly be written in terms of temperature or enthalpy as H 3 minus H 4 or C p times T 3 minus T 4, and we get the net work C p times T 3 minus T 4 minus T 2 minus T 1. Of course, as you know from thermodynamics that we could have established the same thing by saying Q in prime, which is H 3 minus H 2, and Q out prime, which is H 4 minus H 1, and talking about the net heat addition, which is C p T 3 minus T 2 minus T 4 minus T 1, which is the same as W net as it should be. And we can define the efficiency of this Brayton cycle as W net prime by Q in prime. So, this gives us the thermodynamic background of the gas and steam turbines, which we are going to discuss now. And also let me make one point clear, that when we discuss the steam turbine, actually I will talk about with reference to steam turbines, but I am not really considering wet steam. So, my approximation for this work is that I am considering the steam also to behave like a gas, which is possible approximately when we are talking about in the superheated zone. In the superheated zone, the steam can be also considered as a gas with the equivalent properties. Strictly speaking, please note that we need to consider the steam as wet, and more so if we are interested in the low pressure stage of the turbine. But that is a separate discussion, the effect of the wet steam, which I will not do in this introductory lectures on steam and gas turbine. So, first we will start with different types of steam turbines. This is an axial flow simple impulse turbine. So, let us look at the component. The first component you can see is a CD nozzle, which we have discussed in the last lecture. What was the role of the CD nozzle? The CD nozzle actually accelerates the steam from the subsonic condition to a sonic throat and then goes to the supersonic. So, we get a very high rise in the velocity shown by the red line here, and there is a corresponding drop in pressure. Since it is an impulse turbine, and by the definition of impulse turbine we talk about no pressure change should take place in the blade rotor blades. So, we see here that in the rotor blade region the pressure does not change and it is a condenser pressure which is attained. So, the steam enters from here, gets expanded in the rotor blade. You can see the rotor blade is connected to the shaft here and it moves out. So, this is very simple construction. You can see these blade profiles. The blade profiles also deserve some special mention. You see these blade profiles appear like as if it is a plate which is bent in the form of C. Now, you know that in an impulse turbine the angle of deflection or the path that the outflow will take from the blade with respect to the incoming direction, there will be a large deviation. So, this angle of deflection is large, which is the characteristics of impulse turbine. But what about the shape? If you look at the shape is not simple plate of uniform thickness. The plate has more thickness at the center and less thickness at the sides, this at the edges. This is because we do not want the flow to separate here, and then this contouring is very essential. Now, this simple impulse turbine is easy to construct, but then we do not really opt for it. Why? Let us look at the features. The first is the converging diverging nozzles are used, as we have discussed. The steam leaves the nozzles at very high supersonic speeds, typically around let us say 1100 meters per second. These are just numbers to give you a feel for how high the speeds can be. You do not have to consider that this number is very sacrosanct. So, next is the steam leaves the rotor also with an appreciable velocity, you can see. Now, what is the objective of any turbine? The objective of any turbine is, if possible, we should extract all the energy, including the kinetic energy, from the fluid. So, you can think about it like you are trying to extract the maximum energy, and then you see that such a large velocity magnitude is going out as unutilized. Then what happens? If this is not utilized, then the total power that can be produced from the turbine is not properly utilized. So, exit kinetic energy has to be minimized. Like in the hydraulic turbines, for example, we have used the draft tubes. So, similarly, here also this exit kinetic energy from the turbine should be recovered. And the other problem that will come in is that for high efficiency we know that the blade speed should be half of the steam speed. This was already discussed in case of impulse turbine. The other impulse turbine we studied is the Pelton turbine. In that case we showed you, if you remember, that the highest efficiency will come when the blade speed is half of the jet speed. In this case of simple impulse steam turbine, we can say that the blade speed should be half of the steam speed, that is absolute velocity which is coming out of the CD nozzle. So, now if we take the example of number, we are talking about the steam leaving at 1100 meters per second, which means the rotor blade speed, the peripheral blade speed, whatever you call it, should reach 550 meters per second, and then typically we will get a very high rotational RPM. This is not desirable, and because then in that case we may have to use some gearing arrangement. So, because of these two reasons, that is exit kinetic energy loss and for very high RPM, we need to resort to an alternate arrangement for steam turbines. and that is called the compounding of impulse turbine. Compounding, loosely speaking, as I will explain you more in the next slides onwards, compounding loosely speaking means basically staging or arranging the turbines. Okay. I will come to that in the next slide itself. So, we say that the compounding of impulse turbine serves two purposes: one, to reduce the exit kinetic energy loss, and to reduce the rotational speed. And this compounding of impulse turbine can be done in three ways. The first one I call it as pressure compounding, or it is called pressure compounding. The second one is called the velocity compounding, and the third one is called pressure velocity compounding. Now, we will take up each one of these to know the features of pressure compounding, velocity compounding, and pressure velocity compounding. So, this is the schematic of the pressure compounding. Let us look at the structure of the flow here. The steam that comes out from the boiler enters through a CD nozzle, then it goes through the moving blade. You can see M written here, M stands for moving blade, N stands for nozzle, and then it goes through the second nozzle, set of nozzles, and then the moving blade, again the nozzle and the moving blade. So, what does this combination of one nozzle and one moving blade tell you? It tells you that this is one stage. So, we can say that in a pressure compounding steam turbine, whole expansion of steam is arranged in a number of steps by employing a number of simple impulse turbines in series on the same shaft. For example, the first one can be called as a first stage, because we know that a simple impulse turbine has a nozzle and the rotor or the moving blade, and then this is a second stage, third stage, and so on and so forth. So, we can say that a typical stage is comprising of this unit, a nozzle and a rotor. So, this is called a stage, and hence pressure compounding is essentially nothing but the simple impulse turbine in stages. Also, one more point we have to note is that in the nozzle the velocity increases, in the moving blade it reduces, increases again, reduces, and it goes. But what happens to pressure? If you see, the pressure reduces in the nozzles and does not change in the moving blade as it should not change, and then again reduces. And so, what we see, to remember loosely that what is pressure compounding, let us say after few years of doing this course, if someone asks you what is pressure compounding, you should be able to think that pressure compounding means as if the total pressure drop is divided into smaller steps. So, where does the pressure drop take place? In the nozzle. So, in this case pressure compounding means we have one nozzle, and then of course, it should be followed by a rotor. So, that perhaps will help you to remember what is a pressure compounded impulse turbine. And as I said, this is called a stage of a turbine. So, if somebody asks you what does a pressure compounded impulse turbine one stage comprise of, you should be able to say it comprises of a nozzle and a rotor or a moving blade. Let us continue the discussion. Pressure reduces only in the nozzle while it remains constant in the moving blades. Since pressure drop in each nozzle is reduced, steam velocity and hence blade velocity are reduced, and lost kinetic energy is reduced, and it is about 1 to 2% of the initial kinetic energy available. You consider that in the simple impulse turbine it was about 11%, now we are talking about 1 to 2%. Steam on either side of the diaphragm will be under different pressures, and hence there will be leakage from the rotating shaft and the diaphragm holding the nozzle. Let us look at the pressure compounded impulse turbine once again. So, what we are saying is that there is a pressure difference on across the diaphragm, and hence there will be a leakage. So, the leak prevention has to be considered as a major task, and this is achieved by labyrinth packing. This type of turbine is also called Rateau turbine. The next type of turbine we are talking about is the velocity compounded impulse turbine. Look at the first one. First one, it has a nozzle, the same CD nozzle, then it has moving blades, then onwards there is a difference. So, you have a guide blade or the stator, then you have rotor or the moving blade, guide blade and moving blade, and in this way it goes. So, what happens here is, if you see that the pressure reduces only in the nozzle and then it remains constant to the condenser pressure. The velocity in this case first increases in the nozzle and then reduces in the moving blade, remains constant roughly in the guide blade, reduces again in the moving blade, and so on and so forth. Now, in case of pressure compounded impulse turbine, I said that you can try to visualize and remember that a pressure compounded impulse turbine is nothing but an impulse turbine in which pressure is reduced in stages. So, if I use this way of explaining, then what will velocity compounded impulse turbine do? It will try to reduce velocity in stages, and that is exactly what we see in this diagram. So, in this case you have to understand that the first stage comprises of nozzle and the moving blade, but a typical intermediate stage or a typical stage, to say simply, will comprises of the guide vanes and the moving blades. So, stator and the rotor. This is a velocity compounding. So, velocity drop is arranged through many rows of moving blades instead of a single row of moving blades, and it consists of a set of nozzles and several rows of moving and fixed blades, as we just now saw. A stage consists of a set of fixed blades or nozzles in case of first stage and moving blades. So, this is important that only in the first stage, I repeat, there is nozzles, and otherwise it is having the guide blades or fixed blades or stationary blades or simply stator. So, fixed guide blades just direct the flow onto the moving blades and there is no pressure drop. This type of turbine is called the Curtis turbine. So, we have learned two types of compounding. Now, what happens is, if you try to have the pressure velocity compounded impulse turbine. So, what we have? First we have the CD nozzle, then we have the moving blade, then the guide blade, then the moving blade. So far so good. Then what happens is, we start again this process again. So, we have a nozzle, second set of nozzles, and then we have the moving blade, the guide blade, and again the moving blade. So, you see here the pressure reduces in the first set of nozzles, then remains constant, and then again reduces in the second set of nozzles and then remains constant and goes to the condenser pressure. So, here you see the pressure gets reduced twice in the structure we have shown, and both times in the nozzles. So, pressure compounding comes, and velocity also reduces in the moving blade, increases again in the nozzle and goes back to the lost velocity or exit kinetic energy in the second set. So, this is called the pressure velocity compounded impulse turbine. But steam turbine need not be always impulse turbine, and we can have what is known as the reaction turbine. So, in this case of reaction turbine, what we have is the general case, like what we have is, we have a stator or stationary blade or fixed blades or the guide blades and the moving blades. So, we have the usual way of fixed blades, moving blades, fixed blades, moving blades, and so on and so forth. So, you see in this case the pressure reduces in the fixed blade, in the moving blade, fixed blade, moving blade. Why? Because in reaction turbine there is no restriction that pressure should not reduce in the moving blades. And you can also see the deflection angle is not as significant as in the case of the impulse turbines. The blades are not so highly curved. This is also we have discussed in connection with the degree of reaction and the blade curvature. Try to connect that discussion we had on the blade curvature and degree of reaction with today's practical example we are talking about. So, this brings us to the end of today's discussion on the classification of turbines, the steam and gas turbines, particularly the steam turbines. So, we can say that we in this today's discussion, we have talked about the layout of steam and gas turbine plants and identified the essential components. We talked about the Rankine cycle and the Joule and the Brayton cycles that are used for vapor power and the gas turbine operations respectively. We talked about different types of axial flow steam turbines. We started with a description of a simple impulse turbine. We talked about the problems associated with a simple impulse turbine in the form of very high speed and giving rise to lot of large exit kinetic energy loss. Then we talked about the compoundings, the pressure compounding, velocity compounding and pressure velocity compounding, and then we talked about the reaction turbines. So, I will stop here for today's discussion, and in the next class we will talk about how to represent these operations of these turbines in the thermodynamic HS plots, and also talk about how to connect with the velocity triangles, which you have learnt in the earlier part of this module. Thank you.